Okay, so let's start with this lecture on statistical tests. Last time we saw a bit of information about hypothesis testing, so a bit of background on the topic of controlled experiment and hypothesis testing, and I mentioned several times statistical tests, telling you that there were black boxes that basically produce a value that is the test statistic, and another value that is the p-value that is useful for you to assess whether the null hypothesis can be rejected. Today you will see some examples of tests. Still, they will remain a black box for you, but you will understand a little bit more when to use a specific test. Of course, again, this lecture is giving you pointers to information, because the field is very large, it's huge. So you will need to often, when you design experiment, resort to books and resort also to guidelines for performing statistical tests, because every time you build an experiment, it becomes easier to automate certain procedures, but you always have to rely on some external material to understand which specific test to use for your specific experiment. Okay, so let's start with a very brief summary. I try to compress everything in one slide for about the last lecture. What did we learn in last lecture? In last lecture, we learned that every experiment produces a test statistic. Every time I do an experiment, I take my data and I produce a test statistic that is a numerical summary of my data. So a number that somehow summarizes this data. And then we spoke about the null hypothesis. Every time I perform an experiment, I need to express the null hypothesis. That is the negation of the hypothesis that I want to support. Okay? Then what I do is imagining to perform a set of experiments in a population in which this null hypothesis is true. I perform this set of experiments, and for each experiment, I compute my test statistic. The distribution of the test statistic for this population in which the null hypothesis is true is the one that you see in the slide. So the distribution is centered in the value that the test statistic has when the sample confirms exactly the null hypothesis. And you have to consider why this, because if in the population the null hypothesis is true, if I take many samples, it is very likely that this sample will fall around the value of the test statistic when this value confirms, when the sample confirms exactly the null hypothesis. In this population, the majority of the sample will be around the center of this distribution, while very few samples will fall in the tails of the distribution. Actually, what I want to show is, what I want to show in this case is that in this case, I performed just an imaginary experiment. And I want to show that my actual experiments, the one that I made with my data, is producing a test statistic that does not come from this population in which the null hypothesis is true. Okay? And I want to show, therefore, that my test statistic will fall on one of the tails. For this reason, I define a certain significance level that is called alpha. Alpha is an area that is associated to the test statistics that for me will be acceptable for rejecting the null hypothesis based on my data. Okay, so I establish this alpha value, normally 0.05. Then, at this point, everything is performed in theory, because I have made an imaginary experiment somehow, and I have decided a value of significance beforehand based on the risk that I can take. This, we saw it in the previous lecture. I'm not going through that, but the thing that you should remember is that this alpha in software engineering experiments is always set at 0.05. At this point, I perform my experiment and I perform my statistical test. My statistical test will lead to a p-value, will produce a test statistic value and a p-value. The test statistic value is the point in the x-axis that is indicated here. So this point is my test statistic value that is derived from my data. This point will produce, as a byproduct, a p-value, a blue area that I can compare with the alpha area, so with the area that I depicted before. If this area is smaller, so if the p-value is lower than alpha, then I can reject my null hypothesis, because it means that my sample, my specific sample, would be so rare in a population in which the null hypothesis is true that is more likely that the null hypothesis is false. Okay? So this is to summarize just in one slide what we saw through the different slides of last lecture. Now let's pass to statistical tests. So we are speaking about this production of the test statistic, the production of this number, the production of P, but we didn't go through what are statistical tests. And we just mentioned the t-tests several times, but we didn't show how it works. So let's go through the slide. A statistical test is a means to establish a test statistic, which is a single value derived from the data of my experiment. This we already know. There are several tests, and each one is appropriate for the specific type of experiment. So the choice of the test will depend on your design. There are two main categories of tests that are parametric and non-parametric tests. The parametric test makes some assumptions on the population distribution, and most of all, normality. And the non-parametric tests do not make assumption on the parametric distribution, on the population distribution. In most of the cases, for each parametric test, there is a non-parametric alternative. Normally, we start, if possible, from parametric tests. Why? Because parametric tests, they have more statistical power. This is a concept that we did not consider last time, but basically is related to the value of beta and indicates a more statistical power that is associated to parametric tests, indicate that these tests are more likely to lead to the rejection of the null hypothesis when it is false. What does it mean? It means that if the null hypothesis is false in the population, then you get lower p-values. That is actually what you want. Okay. The issue is that when you have nominal or ordinal data, you cannot use parametric tests. And also, you cannot use them if the assumptions of the parametric tests are not satisfied by your data. And among this assumption, the most common is normality, but you can also have some tests that ask you for homogeneous variances of the sample. The non-parametric tests do not make an assumption on the distribution, so they are more robust, but they are more likely to lead to some type 2 errors, so to being unable to reject the null hypothesis, although this is false. They can be used, however, on nominal and ordinal data. So in this case, you have no choice, basically. When you perform a parametric test, as I said, you need to check that your data follow some assumption. And the main of this assumption is the normality of your data. For this, you need to perform a test. You need to perform a test that is the normality test. This is, again, a statistical test, so a black box that produces a number and that allows you to reject the null hypothesis. Okay? It is peculiar. It is peculiar because for the normality test, while for the other tests you look for very low p-value, for the normality test, the null hypothesis is the population is normally distributed. And you actually want to show that the population is normally distributed. So what you aim to is to is to have high p-values, okay, and not being able to reject the null hypothesis. So, okay, normality test, there are several. I'm putting here this slide because it is very important to check the assumption of the test that you'll be doing, and I'm showing this beforehand, before discussing any test, because very frequently people do not consider the assumption of a certain test, while this is very important, especially in software engineering. So I'm discussing this as a first thing. Why they are particularly important in software engineering? Because in other discipline, you may have larger samples. When you have a very large sample, the normality assumption normally holds. Okay, so while in software engineering, when you have more than 30 samples, you normally are safe. Okay, software engineering, this does not always happen. So sometimes you have lower samples, so you need to assess that there is a normal distribution there. So what you do in these cases is choose certain statistical tests. For normality, you search in the list of possible normality tests. I will show you then some references, but it's very easy to find to Google normality test, and you find a long list. And if your p-value, if you perform this test and your p-value is higher than the chosen alpha level, you are safe. Normally, in this case, you will choose the alpha level instead of 0.05. You will choose 0.1 because you want to fall in the central area of your distribution. You want that your sample is closer to produce a test statistic that is closer to the test statistic in the case of in that case in which the null hypothesis is true. So there are also ways, if your data is not normally distributed, there are also ways to transform your data. This is frequently done, but is not so recommended. So I'm not recommending it here. The best thing that you should do if your data is not normally distributed is to check for outliers. So to check for values that are really different from the common values. Why? Because these may be due to several reasons and may jeopardize your results, especially if you are dealing with a small sample. The several reasons may be if you are involving subjects that some subjects do not really perform the experiment in an appropriate way, do not respond to the questionnaire associated to your experiment with sufficient care. There may be several reasons, especially if you perform these experiments with students, because as we said last time, students are the most source of subjects in software engineering experiment. Another remark on non-parametric tests here, the distinction between parametric and non-parametric tests, is that in parametric tests you have to check assumptions, and if you aim to use a parametric test you have to check assumptions. These assumptions are normality assumptions, but also other assumptions that you have to check every time you consider that test. Non-parametric tests are the alternative tests that you use when the assumptions do not hold, or when you deal with categorical or ordinal data. Okay, so before doing any test statistic, if you want to use a parametric test, you need to do these preliminary tests to assess that there are different assumptions hold. Please be careful that also non-parametric tests may have assumptions too. Here I have a link in which there is also the list of assumptions for non-parametric tests. But here the thing that you have to remember is that in most of the cases, if you have a sample that is sufficiently large, it normally follows a normal distribution. On the other hand, if this normal distribution does not hold, you have alternative tests. Okay, and the assumptions for the alternative tests are normally weaker. So now let's go to the selection of the right test. In this case, in this guide, I will show you a diagram that is basically a sort of flow chart that allows you to guide to the choice of the right test. In this diagram, I will consider to have just one dependent variable. This is because, as we said also last time, it is important that an experiment in software engineering is manageable. So it has a manageable size and control, and to do so, the most common thing is to have just one dependent variable. Okay. The selection of the tests depend on several factors. First of all, the type of dependent variable that can be nominal, ordinal, or scale ratio. So scale and ratio, they all allow the same type of test. On the type of hypothesis, that can be, as we also consider, either relationship or relationship, association, or difference. The number of treatments that I'm considering, so the possible values of my independent variables, the type of design, and the number of independent variables. So several factors. You don't need to memorize neither these factors nor the entire flow chart. Okay, no, you don't need to memorize the diagram, but you should know how to follow it. And I think that the example will help. I will also not explain how each test work, because I think that since these tests in the end will be push button tests for you, it is more important to know which are the cases when to use a certain test and to know how data should appear for this test, because the rest of the procedure is straightforward. As I said last time, the difficult and creative part is in the construction of the experiment and coming from the hypothesis to the data, but the other part is mostly automated. Again, in this case, our test is again a black box producing test statistic and p-value. We will see a little bit more of this of one of these black boxes, but not so much, and I leave some of the slides as a curiosity for you, because discussing them would be too long. Okay, so this is the half of the flowchart. The flowchart is very large, and you see that it allows you to choose a certain test based on certain features, on certain characteristics of your experiments. Okay, so that's why the tests depend on the experiment design. So first of all, I look at the type of dependent variable. We said there is just one dependent variable. Okay, so the variable can be nominal, ordinal, or interval-ratio. Nominal, labels; ordinal, order labels or numbers. Okay. For the first cases, as we said, we can use only, so for nominal and ordinal variables, we can use only non-parametric tests, while for the other cases, we can use parametric tests or non-parametric alternative. In the diagram, I have put the non-parametric alternative in italic below the parametric test. How to read this is quite intuitive. I can go also backward in the previous slide. So you start, you check in the box what is the feature that you want to consider, for example, the type of dependent variable. Then you check the following feature that allows you to choose a specific test. This list of tests is not exhaustive. Okay, it is important that you remember that. And there are many more tests and many more alternatives, but these are the most important tests that you will encounter and that you will need in practice. And anyway, knowing your way through this test, so this test allows you also to choose additional tests and to find additional tests that may be appropriate for your specific case. So let's start. We start from the left part, okay, from the nominal dependent variable. Here, from this slide on, I will use as EV as independent variable and EV dependent variable. I will show you just a list of examples, okay? So in this case, the first example is having a nominal dependent variable, and then I check the number of independent variables. This number can be even 0. This is an interesting example. In this case, the dependent variable is the type of defect, but the independent variable does not exist. And my research question is, to which extent the proportion of defects of a certain type matches the expected proportion? So when can I use this type of question? For example, in a case in which I know that in my company, normally the distribution of defects follow a certain type of rule. So I have some expected proportion of different defects in my code module, and I want to see whether this code module that I'm receiving now has an amount of defect that is comparable to the common level in my repository. Okay, so I compare some observed proportion with an expected proportion for each defect type, and the chi-square goodness of fit will allow me to state whether I am close to what is expected or not. How far am I from the expected distribution? This is used also for normality testing, chi-square goodness of fit. So this is to give you an example and a case in which this can be applied. The other case that is more common is the case in which you have more than 0, so one or more independent variables. And this is the chi-square test of independence. For example, in this case, the independent variable can be the code author, and the dependent variable can be the defect type. The research question is there a link between defect type and code authors? So do some authors tend to do certain type of defects more than others? And here you have the example. So my null hypothesis is that there is no relationship between defect type and code author. So I have here a list of code authors, the Simpsons, and a list of defect type. Here just 2 defect type, null pointer and division by 0. And I have the number of null pointer defects made by Homer. Okay, in the cell, the number 10 is the number of null pointer defect made by Homer. The 34 is the same number made by Liz, etc. Okay, quite clear. I put it as input to my test statistic, chi-square test statistic, and I have a number 56.32. This number doesn't tell you anything, but is the test statistic for the chi-square test. That's when I was, and it is computed based on this number. And the p-value is very low. So I can say the H0 is rejected. So there is a relationship between defect type and code author. As we said last time, we should also check how strong is this relationship. So we should also check the so-called effect size. In this case, the effect size that we should use is Kramer's V. It is a type of effect size test, effect size measure that we did not discuss, but you can check Wikipedia for the type of effect size associated to each test. So finally, I'm not every time I'm not clarifying to you what are the specific guidelines is because the cases are so many that you will need anyway to resort to some external information. And this is another typical case, which is the effect size, typical effect size to adopt for a chi-square test of independence, Cramer's V. And how to do it, you can check in internet, and there are libraries for doing that. Let's go to the central part. So in this case, in the previous cases, we had nominal dependent variable. Here we have ordinal, so ordered labels. And we have a type of hypothesis that considers the difference between two samples, basically. And then I have to check what design did I make. The design can be different group of subjects or single group of subjects. We will see the example. Let's start from different group of subjects, okay? This can be a bit confusing, because when you speak about difference, you suddenly think, okay, I'm checking the difference between two groups of subjects. But I will show you that there are cases in which you may consider even a single group of subjects, but evaluating the difference between different samples anyway, okay? So in this case, the example is what is the difference between the degree of project success between novices and experts? So do novices have more project success rate or degree than experts, or vice versa? Here, the independent variable is the level of experience, so 2 levels, and the dependent variable is the degree of success. And I'm comparing different groups, so novices and experts. For example, as you can see in this table, you have novices that, in this case, we are imagining that we have different levels, so ordinal labels, that I have transformed here into numbers to say the order between the labels. And for example, the first novice of my sample have a very low degree of success, so 1. The second has a degree of success 3. How did I compute this degree of success? Well, this is a way of this may have been chosen during the design of the experiment. The important thing is that here I have established a measure for the degree of project success, and I can compare the 2 degrees of novices and experts. So I have taken 2 groups, and the results of the group of novices for the level of degree of project success is on the left column, and for the experts is on the right column. It's basically comparing these two lists of values. And the Martin-Witness U-test is the one that is normally used. I will not show the results, etc., because it would be similar to what you've seen for the other test, and also the frequency of this type of test is not so high. The alternative is this example here. So in this case, I'm still looking at differences, but I'm looking at differences considering the single group of subjects. So I'm repeating some measure. In this case, I'm using the so-called Wilcoxon-Signet rank test. And the question is there a difference between the performance of the developers between morning and afternoon? So developers are the same, but I'm checking their level of performance, again, unordered variables that I may have estimated in some way, I mean, evaluated in some way. And in each row, I have a specific developer. And I'm measuring the performance of a certain developer in the morning and then in the afternoon. For example, this level of performance may be related to amount of code that is produced, okay, in a certain time frame. So I don't consider how am I choosing the measures for these levels. I'm considering that, again, I have been able to choose some levels. So first developer take a level of 3 in the morning and level of 4 in the afternoon. The second developer takes a level of 4 in the morning and 6 in the afternoon, etc. And I have a list of developers. They are the same developers, just checked in different times. So single group of subjects, repeated measures. Finally, relationship. So before I was checking the difference, and now I'm checking just the relationship. And this is a very simple example. Is there a relationship between the degree of motivation of a person and the degree of project success? Again, we are speaking about ordered labels, so degrees, okay? And again, in this case, I have, for each row here, I have a specific person that has a level of motivation 3 and a degree of project success 10, a level of motivation 3, the second person, and a level of success 3, etc. Okay, I have these two distributions. I have these two samples. These samples associated to each person that I'm considering, and I apply the Spearman's rule to test my hypothesis. So now let's pass to the. Now we've seen the left part of our diagram. Now we look at the right part. In the right part, we are considering a dependent variable that is a number. Here we have another example about relationship, and the research question here is there a relationship between review duration and number of defects identified? What is the difference between the previous case? While in the previous case we were speaking about levels, so an ordinal variable, ordered labels basically. Here we are speaking about actual numbers, so number of defects. Okay, so that's why I need to use another type of test. But the situation is similar. I will have a list of computation that express the duration of the review, so the time that a certain person has dedicated to the analysis of the bugs in a piece of code or in a requirement, and the associated number of defects. For assessing this relationship, I use this type of test. I can have the other case in which I have numbers, but I'm not checking at relationship, but at differences. When I check about differences, I can have, I now look again at the number of independent variables that I have. As before, as in the case, and in the very, very initial case, I can have 0 independent variable. For example, like in this case. In this case, my question is there a difference between the number of defects identified in the models and the mean value expected? So again, I know that my models normally have a certain mean number of defects, and I want to understand whether the models coming from a certain project are in agreement with the typical mean of my population. Okay, and to test that, I can use the z-test or the t-test with single sample. In case you know the standard deviation, you know you use of the population, you use the z-test. You rarely know that, but it can be. And otherwise, you use the single sample t-test. We will see later the two cases of two sample t-tests. But here is very intuitive. What you input is the expected mean and your sample. Then there is the other case in which instead of having 0 independent variable, you have 1 or more. In this case, I have to look again whether I am considering a single group of subjects or different group of subjects, like in the case of the experiment in which I considered novices and experts, and the case in which I consider the same group of people in the morning and in the afternoon. Here we go through the case in which I have just one single group of subjects, so I'm performing repeated measures. Then I have considered the treatment. The treatment, of course, they are at least 2, because I'm repeating the measures, and but it can be also more than 2. Let's say when you have exactly 2 treatments. Here is the example. I have as a treatment, as possible treatments, 2 tools, okay? And I want to assess whether a certain tool, or in this case is the presence of a tool or the absence of a tool, actually, sorry, And the dependent variable is the speed in finding bugs. And I want to understand, this is very typical, does the tool improve the user speed in finding bugs? That is better expressed, considering that I'm checking hypotheses that speak about difference, is there a difference in terms of speed with and without the tool? So this is the difference that I'm looking to. Let's see this example a bit more in depth, because it's quite informative for it's quite informative also for understanding everything that is behind also the construction of an experiment. Per t-test has several names, and can be called also repeated measures t-test, paired samples t-test, match pace t-test, etc. So you find it with several names, but all these names are referring to the same thing, the paired t-test. So let's consider this case in which I have this new tool that support bug identification in code review, and I want to understand whether it is effective or not. So the question is, does the tool improve the user speed of finding bugs? So during the code review, you can rely on this tool instead of doing the bug checking by hand, for example, through a checklist. Okay. In this case, the independent variable is the tool, the presence or not. So tool, yes, no. And I have, of course, two treatments. Two treatments are the one treatment with the tool and one treatment without the tool. So manual assessment of the bugs. The dependent variable is the speed. How do I define the speed? I decide that the speed, bug finding speed, is given by the number of bugs found per minute. Okay, this is a choice that I make. And my hypothesis is the speed without the tool is lower or equal to the speed with the tool. This is the hypothesis, of course, that I want to reject, because I want to show that by using the tool, you become faster in identifying your defect. How is it my design? This may be obvious to you, but it's not always obvious. First of all, because using a tool puts an overhead on the people, and the people may be quicker in some cases in spotting out defects without a certain tool, because the tool may produce many false positives, for example, bugs that are not bugs, and you look at them and you have to spend some time in understanding why the tool produced that type of result. So it's not let's say a dumb experiment. It's an experiment that makes sense. How do I design it? I take 13 users, and I have one code file to review, and I ask them to do the bug search without the tool, so treatment, no tool, manual treatment, and then search with the tool. Then I compare the speed for each user in the two tasks and see if they improved. So if they improved between the treatment of not manual treatment and the tool treatment, let's say. You see that there is a problem in this design. The problem is that there may be the so-called learning bias. So we will speak later on about the threats to validity in the experiment, but it's good that you start learning about them already from this example. If I am using the same file, because I'm saying one code file to review, students will do the review without the tool and will check for bugs. But when they will take the tool and check for bugs, they already have some confidence with the file. They will already know the bugs that they are going to find, because they already used the tool before. Therefore, there is a learning bias. Of course, if in this case you are favoring the usage of the tool with respect to the treatment without the tool, because when they will use the tool, they will have already learned about the defects in the code. So what to do? Let's correct this example. Let's take again the 13 user. Let's take again one code file to review. But I want the students or the users to do the bug search with the tool, treatment tool, and then without the tool. And then I will compare the speed for each student in the two tasks. In this case, the learning bias is in favor of the no tool treatment because they do this activity afterwards. So if in this case I see that there is an actual difference in favor of my tool, of the treatment with the tool, it means that I can be quite confident that the tool increases the speed because it was used without knowing the bugs before the manual treatment. So there was somehow a treatment of favor for the manual treatment. Of course, it is not perfect because still I'm using just one code file, and it is true that if I have already seen the defects, I can spot them out much more easily. So I may risk really to say that the time that they employ without the tool is the same, or it's even faster. So let's correct again the design, and in this case, let's take two files, one file X and Y, that are equivalent, so they are comparable. They are the same number of bugs, but they are different. In this case, I will use file X with the tool and file Y without the tool. In this case, I am more confident that the first treatment does not influence the second treatment, so they are really completely independent. But the issue is that there are other issues, of course, because if the task takes too long, the students may get tired of the second task. So the task that I do first has an impact on the task that I do as second, because they maybe stay there for a couple of hours, and of course the second hour will be harder to keep focus. So the effect of fatigue needs to be considered, and I may need to do the treatment in a separate day. These that are like scientific reasons so lead you to modify your experiment in logistics terms. So this is to indicate that even small things related to the theoretical design have an impact on the practical execution of the experiment. Okay. Let's go to this pair t-test, and now we have adjusted. Now we have considered two completely independent treatments in which without the tool and in which treatment with the tool is performed on a specific day and on a specific file, and the manual treatment is performed on another day and on another file. The users are the same, so I take my user and I let them do both treatment, and this number are the bugs per minute, so the speed by the certain tool, without the tool, and with the tool. So I list this number, and I input the number to this black box that is my t-test, and the output is my t-value, that is 3.24, and the p-value is very low, so it's 0.00 something. Here I give you a curiosity. I will not go through the next slide, but I invite you to have a look at it. I invite you to have a look at it because it may allow you to understand better how it works, this magic of computing the statistic, okay? Here are all the computations that are made for computing the statistic in the paired case. And how to read this. On the left you see the numbers that you got from your experiment about the actual speed. Then you have some kind of computation. You have the mean, you have the difference between this value, and you can check 6 minus 3 is 3. Then you have another computation that is dev, that is the difference minus the mean of the other value. And then you have the square of the same value. You do some computation and you obtain your t-value. And the formula is here. You can go through the formula if you are interested. Here you have the number if you want to understand more. So that you see that there is actually no magic. These programs that are computing these values, they actually follow some algorithm as expectable. Let's go ahead. We will not consider too much these aspects, but let's go ahead a bit. In this case, again, I'm considering differences. I'm considering differences. I have one or more independent variable. I have, again, a single group of subjects, so I'm repeating the measure with the same people. And the treatments are more than 2. So in the previous case, I had just 2 treatments, without the tool or with the tool. In this case, for example, I want to compare 4 different tools. So tool A, B, C, D, in terms of speed of bug detection achieved by the user. So same dependent variable, so bug detection speed, more tools, and a set of users that first they're using tool A, then tool B, then tool C, and then I check the speed that they achieve. Now let's pass to the case in which I have a different group of subjects. And therefore, I'm not doing repeated measure on the same subject, but independent measures, completely independent measures. For example, this is an interesting example, and I will show you, and we will go more deep into the characteristic of this case. The question here is, does the tool improve the user speed in finding bugs? Is there a difference? And again, this is a difference. So is there a difference in terms of speed with and without the tool? In this case, the case is very similar. Is very similar to the one before. But let's see some difference. So let's see the difference here. Basically, the problem is the same as for the pair t-test. Okay, for the unpaired t-test. But in this case, I'm focusing on completely getting rid of the learning bias and the fatigue effect. And I have been able to recruit a lot of users. So I'm not asking the users to do their experiment first without the tool and then with the tool. And I've taken a large amount of users that have a comparable competence, because of course I have to control their variable, the level of competence, and I change my design, and I have 2 groups, and I randomly allocate subjects and assign them to one of the treatments. Some of them will do the manual activity, and some of them will use the tool. Of course, as it's written here, I have to assess that the level of competence is comparable. To do this, I can do the so-called pre-test, which is a test that I have to design, a questionnaire, for example, or a system for evaluating that actually their average degree of competence in finding bugs is comparable between the different subjects. Otherwise, if I don't want to do this pre-test, but it is always recommended that you do because it is evidence that allows you to do some statement. Otherwise, you can provide some arguments that all your subjects, they have more or less the same degree of competence because they are people coming they are students taken from your course, from the same course. They are all novices, and therefore I can say that the results that I obtain are valid for the specific category of users, so student, novices, people that don't have so much experience with the review. So my tool is more appropriate, let's say, is particularly appropriate for novices, because this is the population on which I tested my tool. The 2 groups in this case, while in the previous, one thing that you should notice here is that the 2 groups need to be balanced, but you do not need to have the same exact number of people in the 2 groups. So if you have 25 people, they can be divided into 13 and 12 subjects, because here I'm comparing the means of the sample, and I don't have to do in practice a pair comparison. So you have independent samples, so they can have also different number of elements in each one. Of course, need to be balanced. You cannot have a sample with just one subject and the other with 20. It goes without saying. But a little bit of imbalance can be accepted. This is the Ampere t-test. In this case, instead of having the same users as before, so just the 13 users, I have these 26 users, and I put the same number, exactly the same number as before, for the t-test. But now the users that are using the tool are completely different from the ones that are not using the tool. In this case, I do my computation for the unpaired t-test, and I see that t-value is different from the one that I obtained in the previous case, although the numbers are exactly the same, but they come from different subjects. Okay, so they come from different subjects, and I have to consider this in the test that I am choosing, because this has an impact both on the t-value and consequently on the p-value. What calculations are made to find this t-value? So what calculation are made? Also, in this case, I will just show you the slide to show you that there's no magic again. The calculations are more complex, of course, but to read this slide, and I invite you to do at home, you look at the left part, in which you have the case, the list of data that you have for the users that did not use the tool, the set of data that you have for the users that use the tool, and several computations that are related to the difference between the values that you have and their mean, the square differences, and several other computations that also involve the degree of freedom. The degree of freedom we didn't touch this topic, but is a number that is related to the size of your sample, is the df here. If you want to understand what is it, you just look into other resources. But here is just to give you some indication that the t-value calculation also in this case is something that can be performed even by hand. And you don't need, in principle, a software for doing that. But in general, you will always use a software for doing that. Normally, since you are computer scientists or mathematicians, you will use R. What about the effect size? In this case, I am computing the differences, so I will use the Cohen's d. These are the numbers that you need to compute the Cohen's d. And the number are the mean of the value and the standard deviation computed on the sample for both the case with the tool and without the tool. And the formula of the Cohen's d is there as it was before, and this is the value that you obtain, so that you can say that you have a small to medium effect size. And this how was done by looking into Wikipedia, where there was the table of the different Cohen's d. So the computation, if you see this number, if you see these numbers here, can be done by subtracting the different means. You see the value are the same, divided by the average between the two standard deviation.